Moving fluids form complicated patterns. These patterns are often quite surprising. What appears to be a small shift in system geometry can change the entire flow pattern. But it is almost never possible to predict the real flow pattern on theoretical grounds alone. We need other approaches. One of the most efficient is flow visualization, direct observation of the flow field. Visualization is an important tool in establishing flow models as a basis for mathematical models. We can use it for direct solution of engineering problems and also as an aid to understanding the concepts of fluid motion. An open surface water channel, such as you see here, is often used in flow visualization. It consists of an inlet section which distributes the flow evenly, fixed outer walls, and adjustable inner walls so that we can achieve any passage shape desired. The flow leaves through a porous exit section to give an even velocity profile. There are a number of visualization methods that can be used with a water channel like this. We can use dye injection. We can use surface powder on the water. First thing we're going to use here, however, is the hydrogen bubble method. If we connect a DC voltage to a very fine wire, here 2 mils, and put the wire in the water, electrolysis forms extremely small hydrogen bubbles which are swept off by the flow. Most of these bubbles are small enough so that they follow the flow quite accurately. A few large bubbles are also formed. We ignore them in observing the flow pattern. Here you see a probe with multiple thin fingers which makes many fine lines. Another kind of probe is a single wire with sections insulated so that we see bands of bubbles coming off the probe. In order to interpret flow pictures, we need to be quite clear about 4 concepts. These relate the pictures to the kinematic description of the flow field. The first concept is the path line. A path line is the trajectory or path of a given fluid element. Here we mark a small element with bubbles so that we can follow its path. If we took a time exposure, we would make the entire path visible. Instead, we superpose a path line, and you can check for yourself that each of these squares follows it. A streak line is a little different. It is the instantaneous locus or trace of all the fluid elements that pass through a given fixed point in space. If we run a short, uninsulated section of a bubble wire steadily, it shows us a streak line. In steady flow, each particle coming past the fixed point moves down the same path, and therefore the streak line is identical to the path line. We can check this by resuperposing the path line you saw earlier. Often it is useful to use multiple streak lines to observe a flow field. We can make them with the multiple finger wire you saw before. The third concept we need is the timeline. A timeline is defined as the instantaneous location of a line of fluid particles marked earlier at a prescribed location in the flow. These lines are usually most useful if the marking location is normal to the flow direction, since then the location of the timeline, a short time later, shows the velocity profile of the flow field. Here we apply the timeline technique to a steady flow past an airfoil. Near the angle which gives zero lift, the portion of the timeline passing above the airfoil rejoins the portion passing beneath at the trailing edge, except for the narrow boundary layer region where the flow is retarded by friction. Since the distance around either side of the airfoil is approximately the same, the timelines show that the average speed above the airfoil is approximately the same as beneath it. When the airfoil is set at angles which give large lift, the portion of the timeline passing above the airfoil outruns the portion beneath. The velocity is higher near the upper surface. At negative incidence, the effects are reversed. The fourth concept we need is the streamline. A streamline is defined as any line that at a given instant is everywhere tangent to the velocity vectors of the flow field. The streamline is essentially a mathematical idea and is very useful in many fluid flow analyses. But there's no way to make a streamline directly visible. You've seen that in steady flow, the path line and the streak line are the same. And you might suspect that the streamlines would coincide with them also. This is in fact the case. Consider a particle moving along in steady flow. As you saw, each particle moves down the same path line, so that it's always moving down this path towards the particle ahead of it. This means it is always tangent to the path, and that is how we defined a streamline. So in steady flow, the streamline, the streak line, and the path line are all the same, and we can use either streak lines or path lines to show us the streamline pattern. Another thing we often need is the velocity vector field itself. We can find the velocity field by using what I call combined time streak markers. The bubble squares you see here are such markers, and they have a number of useful properties that you can prove for yourself. The sides of the markers are streak lines. In steady flow, the sides show the streamline pattern. The fronts and backs of the markers are timelines. In a two-dimensional incompressible flow, the area of each marker is forever constant. Since the time interval for a given marker to pass any fixed point in space is also constant, the length from the front to the back of a marker at any location is a measure of average velocity in that region. Now consider for a moment an unsteady flow, like the one you see here past an oscillating plate. Do you think that in this case the streak line or the path line will be the same as the streamlines? Let's look at a path line and see. Here is a single marked element entering at a fixed time in the cycle of a plate. As before, we superpose its path line. Now compare the path line with a succession of instantaneous streak lines entering through the same point. None of the instantaneous streak lines coincides with the path line. Here is a second element.